Okay, hello, welcome. In this video, we're going to be integrating some quotients. We're going to be doing some partial fraction decomposition, maybe a little bit of UDU, and just some other fractions that we're able to integrate. Okay, so let's get to it. All right, so the first one's going to be 1 over x squared minus 1. So I'm looking at that thing, and I'm seeing the denominator is factorable. Pretty easily factorable. So I know that that's going to be partial fractions. Also, because when I factor it, I don't get two identical factors. It's not a perfect square in the denominator. Let me look. I don't think we have that happening on this homework, but it will be something we run into later in maybe in a couple of classes. So for now, I'm saying factorable partial fractions. So I'm going to break this down. 1 over x squared minus 1 is equal to some number over x plus 1 plus some other number divided by x minus 1. Okay. I'm going to say I'm going to multiply both sides of the equation by x squared minus 1 or by both of these factors. It's the same thing. And that's going to give me 1 equaling a times x minus 1. Yeah. Because when I multiply this fraction by x plus 1 and x minus 1, the x plus 1s will cancel. I'll be left with x minus 1s. And b times x plus 1. I'm going to let x equal 1. And then I'll get 1 equaling 0 a's plus 2 b's. When x is equal to negative 1, I'll get 1 equaling negative 2a plus 0. So I've got a equaling negative 1/2 and b equaling positive 1/2. Okay. So now what I'm doing here is I'm anti-differentiating. A is negative 1/2 divided by x plus 1. And b is positive 1/2 for x minus 1. That's how we'd set it up in the first place. Dx, and that's going to be equal to, well, negative 1/2 of the log of the absolute value of x plus 1 plus 1/2 of the log of the absolute value of x minus 1. Okay. If you had to combine these to, write it as a single log, which you don't have to do in AP Calculus anymore, but if you did, you'd say that was 1/2 of the natural log of the absolute value of, okay, the difference of two logs is the log of the quotient. Okay, so it's x minus 1 divided by x plus 1. And I forgot my plus c, but there we go. But this step is not something you have to be able to do anymore. Okay. If you look at some of the old multiple choice questions for this unit, though, you might see the answer choices looking a little like this. And that's something you need to be able to deal with. Anyway, okay, that's 1a. How about b? Integral of 3 over x squared plus x minus 2. Okay, I'm looking at the denominator. I'm seeing that it's factorable. Okay, that's going to be x plus 2 times x minus 1. And that's equal to some number divided by x plus 2 and some other number divided by x minus 1. Okay, so I'll say I'm going to multiply both sides of the equation by x minus 1 and x plus 2 to clear out the denominators, and I'll get 3 equaling some number times x minus 1 plus some other number times x plus 2. I'm going to let x equal 1, and that will give me 3 equaling 0a plus 3b. Now that tells me that b is going to need to equal 1. If I let x equal negative 2, then I'll have 3 equaling negative 3a and 0b. So that feels to me like a is going to be negative 1. And now I'm taking the integral of a over x plus 2 plus b over x minus 1. And that'll be something I'm able to do. That'll be negative 1 log of the absolute value of x plus 2 plus 1 of the log of the absolute value of x minus 1 plus c. But again, if I had to combine these into a single log, that would be the log of the absolute value of x minus 1 divided by x plus 2. Integral of 5 minus x. All right, the actual correct version of 1c is going to be 5 minus x over 2x squared plus x minus 1. I need to figure out how to factor that. That is going to be, let's see. Well, I'm not immediately seeing it, so I'm going to need to split out that middle term. 2 times 1, negative 1 is negative 2. Two numbers that multiply to negative 2 while adding to 1 would be positive 2 and negative 1. Okay, so I need to go over here and split out, okay, so 2x squared plus 2x minus x minus 1. And then I'll factor out the 2x, and I'll be left with an x plus 1. And I'll factor out a negative 1, and I'll be left with an x plus 1. Okay, I factor out the x plus 1, and I have 2x and negative 1. Okay. So I know that this is equal to some number of x plus 1s plus some other number of 2x minus 1s. Okay, whoops. Okay, I'll cover up my factoring work. And then I'm going to clear out the denominator, and that will give me 5 minus x equaling a times 2x minus 1 plus b times x plus 1. If I let x equal 1/2, I'll get, that'll be 0. 5 minus 1/2 is 4.5 equals 0a plus 3/2 b. So 1/2 plus 1 would be 3/2. And so 3b equals 9, b equals 3. And when x equals negative 1, I'm going to have, what am I going to have? Five minus negative 1 equaling a times negative 2 minus another one is negative 3 and 0b, so a is looking like negative 2. All right, this worked out much better than when I did it, having copied the problem wrong. So now I'm anti-differentiating a over x plus 1 plus b over x, 2x minus 1. Okay, I'm going to say that that's negative 2 log of the absolute value of x plus 1 plus 3/2 for the 2 right there, okay, because that's going to come out with the chain rule, log of the absolute value of 2x minus 1 and plus c. And the reason for the divided by 2 here is you think about if you take the derivative of the log of 2x minus 1, you're going to get 1 over 2x minus 1. But then you'll also have to multiply by 2 for the chain rule. So in order to prepare for that, I'm going to divide by 2, so I end up with 3 logs of 2x minus 1. Or 3 over 2x minus 1 when I take the derivative. So I know I have a good antiderivative. Okay, that was the real 1c. Room. 1d is the integral from 0 to 1 of 3 over that denominator that I had wrongfully copied the first time I tried to do 1c. 2x squared plus 5x plus 2. Right. Okay, now let's break this down. Okay, that's going to be 2x plus 1 times x plus 2. And if you needed to see why that was the case, multiply to 4, add to 5, that's 4 and 1. So 2x squared, 4x, another x, and 2. That's 2x times x plus 2 plus 1 times x plus 2. So I know I have x plus 2 and 2x plus 1. Okay. So 3 over 2x plus 1 times x plus 2 is going to be some number over 2x plus 1 and some other number over x plus 2. All right. Then I'm going to clear out the denominator, and I'm going to get 3 equaling 8 times x plus 2 plus b times 2x plus 1. And that's, pardon me, when I let x equal negative 2, I'll have 3 equals 0a, negative 4 plus 1 is negative 3b. Okay, that's promising. B equals negative 1. And then when x equals negative 1/2, I'll have 3 equaling, all right, no b's. Okay, 3 halves of a. Well, what I could do is I could multiply by 2 and divide by 3. And that would give me 6 divided by 3 is a is equal to 2. Now I'm going to be integrating from 0 to 1 on a. And b is negative 1, but I could write it like minus 1 over x plus 2. Okay, I'm going to need an antiderivative here. Minus 1. Hold up, that's not going to be the antiderivative. I almost made the error I told you not to make. I'm going to need to divide by that 2 for the chain rule. Because if you think about it, this comes back 1, right? Let's cover it up. If I was to take the log of 2x plus 1, its derivative would be 1 over 2x plus 1 times 2 for the chain rule, right? So we need that to be a 1. Minus the log of the absolute value of x plus 2 as x runs from 0 up to 1. Okay, that's all right. Makes me nervous, doing integrating from 0 on something that involves log. That could be troublesome. And so it's going to be 1 log, when I plug in 1, I get 2 and 1 is 3. So 3 minus x plus 2 is also 3. Okay. Minus, when I plug in x equals 0, I get log of 1, which is also 0, minus log of 2. And so I got 0 minus log 2 is just going to be the positive natural log of 2. And that was D. Oh, E, okay, we're going to have one that doesn't require partial fractions. And let me copy that one real quick. Okay. Because it's one term in the denominator. One term in the denominator, I can just write that in the numerator as a negative power, distribute it, and be much better off. Okay, so that's what I'm going to do. I'm going to take the x to the 2 in the denominator, and I'm going to say that's the integral from 1 to 2, x to the negative 2 times x minus 4. And then I'm going to use distribution. So that's going to be the integral from 1 to 2 of x to the negative 2 times x to the 1 would be x to the negative 1, and negative 4x to the negative 2. Now, I'm going to want to add 1 to the power and divide by the new power, right? But then that would be divided by 0. So that's natural log of the absolute value of x. And then I'm going to add 1 to the power, divide by the new power, so it becomes positive 4x to the negative 1. Let x run from 1 to 2. And so that'll be the log of 2 plus 4 times 2 to the negative 1. 2 to the negative 1 is half. Okay. Minus, when I plug in 1, I'll get log of 1, which is 0, plus 4 times, well, maybe 4 divided by 1. 1 to the negative 1 is 1 over 1. And, okay, so I've got log of 2 plus 2 minus 4 is going to be log of 2 minus 2. Negative 2 plus the natural log of 2. Okay, and that one didn't require partial fractions. All right, next I've got integral from 0 to 1 of x plus 1 divided by x squared plus 2x minus 3 dx, and I can see that the denominator is factorable with x plus 3x minus 1. So I'm going to say x plus 1 over x plus 3x minus 1 is equal to some number over x plus 3 and some other number over x minus 1. Okay. Then I'm going to clear out the denominators. I'll say x plus 1 is equal to a times x minus 1 plus b times x plus 3. Then I'm going to say when x is equal to 1, I've got 2 equaling 0a plus 4b. And when x is equal to negative 3, I'll have negative 2 equaling negative 4a, which gives me a is equal to also half. Make sure that's right. Okay. Then I'm going to integrate from 0 to 1. I feel like I've done this problem already, but whatever. Maybe it was in the examples. I'm going to go from 0 to 1 of, maybe I'll factor out the halves, right? Because if I put a half on both of these things, I can factor it out of both of them. So that would be 1 over x plus 3 plus 1 over x minus 1. Okay, anti-differentiate. X runs from 0 to 1. All right, so this is 1/2 of ooh, that's going to cause a problem, I think, if we're going to be x minus 1. Yeah, that's troublesome. This is an improper integral. Oh well, it's going to be okay. I'm going to say it's okay, at this point in the course, you say, all right, log of 4 plus log of 0. That's troublesome. So I say this integral fails to exist. Or just say, leave it at that, right? Because it's asking you to take the log of 0. That's not possible. The balance of integration are messed up on this one. It would need to be, say, I don't know, 2 to 3. I think that would be a better balance of integration for this one. But that's as far as we can go. You just have to say it doesn't exist. Because it depends on the log of 0, and we know that's negative infinity or something like that. So, let's see, I'm going to do one more. On this page, 1g, 1 to 2 of x plus 1 over x squared plus 2x. Okay, so this denominator is very factorable. So I will switch up the color. I found my red X marker. Been looking for that for a couple days. And so I'll say, all right, x plus 1 divided by x times x plus 2 is going to be some number over x, some other number over x plus 2. Okay, this one was definitely in the examples. I remember this one. I'm going to say, all right, clear out the denominator, leaves me with x equals negative 2, gives me negative 1 equals 0 minus b. And when x equals 0, I've got 1 equaling 2a. Hold on. This is just not right at all, right? When x equals negative 2, I've got 0a negative 2b. b equals 1/2. And a is also going to equal 1/2. Yeah, I was going to say I don't remember getting that. I just recorded that video today. So, taking the integral from 1 to 2, a over x, b over x plus 2. If I wanted to, I could factor out those halves. Maybe I will do that. And then I'll anti-differentiate. Antiderivative of 1 over x is log of the absolute value of x. Antiderivative of 1 over x plus 2, after I factor out that half, is going to be log absolute value x plus 2. And I'm going to let x run from 1 to 2. Okay, yeah, this should be pretty workable. So it's half of first term is going to be log of 2 plus log 4. Minus, when I plug in x equals 1, I have log of 1 is 0 plus log of 3. And that's going to be suitable for us. Okay, when they put dx in the numerator, it's like 1 over x minus 1, x plus 2. And I have seen ones like this before that are really polite and already give it to you factored. It's really nice. Very generous of them. So, okay, we know that 1 over this thing is some number over x minus 1, some other number over x plus 2. I'm going to clear out the denominator. And say 1 equals a times x plus 2 and b times x minus 1. When x is equal to negative 2, I get 1 equals 0a minus 3b. Right? Negative 2 minus 1 is negative 3b. Okay, yeah, I believe in that. So b is negative 1/3. Then I'm going to have x equals 1. I'll have 1 equals 3a minus 0b, indicating that b is going to be, that's going to be a. That'll be a equaling 1 divided by 3. Okay. So now I'm anti-differentiating a is 1/3. Over x minus 1 plus b is negative 1/3 over x plus 2. Okay, so when I go to find an antiderivative here, it'll be 1/3 of the log of the absolute value of x minus 1 minus 1/3 of the log of the absolute value of x plus 2 with a plus c because it's an antiderivative. Okay, and if you take the derivative of these, mentally to check, it'd be 1/3 times 1 over x minus 1, which would be this thing, minus a third of 1 over x plus 2, which is going to be that thing, so it works. Right. All right, oh yeah, this is one that I did catch before I printed the homeworks. Change the bounds, I just didn't catch the other one. So 1 to 5, 3 over x squared. Okay, I'm glad I have one like this on here. Okay, we need to rewrite this as a power first before anti-differentiating. So I'm going to grab color. Let's say this is equal to the integral from 1 to 5 of 3x to the negative 2. Add 1 to the power, divide by the new power. Let x run from 1 to 5. So I might just factor out that negative 3, because it's going to be attached to both of these, so I can factor it out. And I'd have 5 to the negative 1 minus 1 to the negative 1. Okay. And so that would be negative 4/5 times negative 3 is going to be positive 12 over 5. And that didn't need partial fraction decomposition or any kind of algebra. We just need to remember that we can still rewrite these things as power. Okay, here we've got ourselves another partial fraction problem, because the denominator is already factored for us. Okay, so I see the denominator is factorable. That means I'm going to need to use partial fractions, and I'll say 3 over x minus 1, x plus 2 is some number divided by x minus 1 plus some other number divided by x plus 2. I'm going to clear out the denominator just like always, and I'll have 3 equals a times x plus 2 plus b times x minus 1. And then when x equals negative 2, I'll have 3 equaling negative 3b, giving me b equals 1. Wait, no, that would be negative 1. Let me make sure. Negative 2, okay, 3 equals negative 3b. Yeah, that's going to be negative 1. I've been particularly error prone today, but that's all right. And then when x is equal to 1, 3 will equal 3 times a, leading me to believe that a is equal to positive 1. Okay, so now I'm integrating from 2 up to 3 on a over x minus 1 plus b over x plus 2. Okay, anti-differentiate, so the log of the absolute value of x minus 1 minus, I'll just put in the minus there, log of the absolute value of x plus 2, as x runs from 2 to 3. So now I'm going to let that happen. 3 minus 1 is 2. 3 plus 2 is 5. And then when I plug in 2, I get log of 1. Log of 1 is log of e to the 0, which is going to be 0. Minus 2 plus 2 is 4, so log of 4. So I know that this is going to be log of 2 plus log of 4 minus the log of 5, and the log of 1 is 0, so I'm just going to leave it like that. Okay. What's that? Okay. Okay, cool. This is something that I'm going to have to rewrite as a power of x. So I'm going to come in, I'm going to say, well, this is really 1 over the square root. Oh, wait. See, I don't ever write dx in the numerator. That's not something I would do. But evidently, I think probably 1 year on the Unit 9 test, I had a multiple choice question that had dx in the numerator, and so I just need to make people aware of it. Because I remember somebody asking me one time, like, what's that all about? And I was like, it's just like 1 over the thing times dx. So rewrite plus x to the negative 1/2 power. Okay, and I should be able to use the power rule on this because the derivative of the inside is just 1. So I'm going to add 1 to the power, divide by the new power, and just check to make sure using the derivative, right? So 1/2 of 2 is 1 times 1 plus x to the negative half times the derivative of 1 plus x with respect to x, which is 1. So this is an antiderivative. And so 8 plus 1 is 9 to the 1/2. So the square root of 9 minus the square root of 1. And we could say that's 3 minus 1 is 2 times 2 is 4. Right. The antiderivative of negative 2x divided by the cubed root of 9 minus x squared with respect to x. Okay, this one we are going to not be using partial fractions because of that cube root, right? We've got layers, we've got a composition of functions, layers, and outside and inside. It's going to be u to u, especially because the derivative of 9 minus x squared, the derivative of the inside of the composition of functions, is appearing on the outside, okay? And this one's going to be a perfect match, too, so it shouldn't be too hard to anti-differentiate. So I'm going to let u equal 9 minus x squared, so that du is negative 2x dx, which happens to be exactly what I have. So this integral becomes antiderivative, negative 2x dx becomes du, and I have 1 over the cubed root of u. And we know how to deal with this. We're going to write it as a power of u. And we can anti-differentiate u to the negative 1/3 with respect to u. We're going to add 1 to the power, so that'll be u to the positive 2/3. We're going to divide by the new power, so that would be dividing by 2/3 is like multiplying by 3/2. And we're going to add a plus c, and then at the very end we're going to substitute on that u, because this antiderivative with respect to x should probably depend on x. So 3/2 of 9 minus x squared to the 2/3 power plus c. M is integral from 1 to e of x squared minus 1 divided by x. Did I not already do this one? Okay, this must also be on the examples because I've done this problem today. Okay, we're going to divide by x, so we're going to, kind of just rewrite this with x squared over x is x minus 1 over x. As long as x is not 0, but if x is running from 1 to e, we don't even have to worry about that. So I'm going to anti-differentiate. Let x run from 1 to e, so that's e squared divided by 2 minus the log of e. E is e to the first power, right? So the log of e to the first is going to be 1. Then when I plug in 1, I'll get 1/2 minus the log of 1. 1 is e to the 0. Okay. So the log of e to the 0 is going to be 0. And so I get e to the 2 divided by 2 minus 3/2, so I could write it like that if I wanted. But if it was free response, you'd be perfectly fine to stop right there, right? That's m. And this one. It's a pretty robust problem set here. Right. This will be, again, because of the layers, or the derivative of 1 plus sine theta being cosine theta, or the fact that it's got trig in it at all, right? We can't factor trig. Well, not trig that looks like this. And so I think we'll just kind of go for it. U is going to need to equal 1 plus sine theta, because the derivative of 1 plus sine theta with respect to theta is just going to be cosine theta, and I'll have a nice match, and it'll be great. All right, so U is 1 plus sine theta. Du is cosine theta d theta, which happens to be exactly what I have. Okay, when theta equals 0, u is 1 plus the sine of 0. Sine of 0 is 0. So that'll be 1. And then when theta equals pi over 2, that gives me u is equal to 1 plus the sine of pi over 2. Pi over 2 is up at the top of the unit circle, so that's where sine is equal to 1. So I've got 1 plus 1, that's going to be 2. Okay. Now with all of this, I'm ready to transform this into an integral that I am much more able to take. So this will be the integral as u runs from 1 to 2. Du is cosine theta d theta, so all of that's gone, and all I have is a du. And now I have 1 over the square root of u. So that's u to the negative 1/2. Okay, I'm going to add 1 to the power. Negative 1/2 plus 1 is 1/2. Divide by the new power, and let u run from 1 up to 2. So this would be 2 square root of 2 minus 2 times the square root of 1, which would just be that. And I'll just leave it there like that. Okay. Oh. Integral from 1 to 2 of, oh, okay, that's good, x squared minus 1 over x plus 1 dx. I'm going to have one of these in here too. So this is one where it's bigger on top, so I'm thinking I need to divide this, okay? I need to divide it before I anti-differentiate. It's not partial fractions, right? It needs to be factorable in the denominator for us to do partial fractions. But this one, I can actually split x squared minus 1 up into x plus 1 and x minus 1. And, we know that integration can be extended to functions that have removable or jump discontinuities in them. So it'll be fine. This is going to be a removable discontinuity because we can cancel off the x plus 1s, but I'll just maybe take this off to the side right here and show you that that's, okay, x squared minus 1 is x plus 1 times x minus 1 divided by x plus 1. And that'll be gone. Okay. And now I'll just have x minus 1. Okay, so this would have a hole at x equals negative 1, which is not even in our region of integration. If that was, it still wouldn't matter because the amount of area we would take out beneath that hole would be basically 0. So, you know what I'm saying. So we will rewrite this integral as the integral from 1 to 2 of x minus 1 dx. And, well, that seems pretty friendly to us at this point. 1/2 x squared minus x as x runs from 1 to 2. Okay, half of 2 squared is half of 4 minus 2. Okay, 1/2 minus 1. And okay, for your response, we're safe to stop there. But that's 0 minus negative 1/2. And that would be positive 1/2. Right. Just got distracted by receiving an email or something. Shouldn't do that while I'm actively recording. But okay, P. Oh yes, this one. I know where this came from. I was copying problems from the examples, or I was copying example problems from the homework. I don't know what I was doing. But I definitely remember this one. 5 over 1 plus t squared dt. This is a multiple choice question for sure. And this is one that we just kind of got to know the antiderivative of. Maybe not 5. It's like, oh man, I know the antiderivative of 1 over 1 plus t squared with respect to t, but what do I do with that 5? I'm going to factor out the 5. This thing that I've boxed off, that's arctangent of t. Okay, and that's just one that we need to know the antiderivative of. We can't factor 1 plus t squared or anything like that. There's not going to be able to split it up into partial fractions because we can't factor it. And so I think that's all we can do is know the rules that we're supposed to know for that one. Okay, finally, I have broken out of the algebraic examples. I've got one more page worth of examples here. And, all right. Okay, find the area of the shaded region without a calculator. Well, looks like we're going to need to be breaking this down with partial fractions because this is x plus 3, x plus 2. Okay, so I'm going to set up that integral. Integral from x equals 0 to x equals 1 of f of x dx. Well, to save myself some time, I'm going to break this thing down into partial fractions first. So I think I already had something written on it. So we're going to say 12 over x plus 3, x plus 2 is some number over x plus 3 and some other number over x plus 2. Okay. I'm going to clear out the denominator. Let x equal negative 3. And then 12 will equal negative a. So a feels like negative 12. And then when x is negative 2, I've got 12 equals b. So b equals positive 12. So now I'm ready to write this as, okay, a was negative 12. So negative 12 over x plus 3. And then b was positive 12, so plus 12 over, what was that one? X plus 2. Okay. So then, lost myself. Anti-differentiate. Let x run from 0 to 1. So when x is 1, I've got negative 12 log 4 plus 12 log 3. And then when x is 0, I'll have negative 12 log 3 plus 12 log 2. And for our purposes, that's just going to be the area of the shaded region. All right, now we're going to find the perimeter of this region using a calculator. Okay, based on the graph, you could go up here and look. This vertical side length is going to be 2. That's going to be 1. Okay, this looks a whole lot like 1, but we need to check and make sure that's 1. So let's see what the value of f of x is when x equals 1. It's 12 over 5, and 1 is 6, and 6 is 12. Okay, so it is 1. Right? So I'm confident. I'm going to say that's 1, and this is f of x. Okay. Since f of x equals the power, so it would be 12 times x squared plus 5x plus 6 to the negative first power. I'm going to need f prime to run the arc length, right? Because we know it's the integral of the square root of 1 plus dy dx squared. So negative 12 times this to the negative 2 times the derivative of the inside is 2x plus 5. Can't even see that. But OK, that'll be what I need to run through the calculator. So my arc length will be 2, 3, 4. Well, I guess the parameter 4 plus the arc length integral, which is the integral from x equals 0 to x equals 1, the square root of 1 plus f prime of x squared dx. I'm going to grab a calculator. Okay, not sure. Oh, okay. Not sure what's going on here. Let's just. All right.
Mr. Huff?
Yes.
Should I take the...
And so me personally, I think I want to type in f prime of x into y1, so I can just do y1 squared, so I don't have to type all this in, make sure I'm squaring the whole thing. I'm going to say it's negative 12 times x squared plus 5x plus 6 to the negative 2 power multiplied by 2x plus 5. Okay, that's dy dx. Okay, now I'm interested in doing 4 plus the integral from x equals 0 to x equals 1 of the square root of 1 plus dy dx I plugged into y1, dy dx squared dx. Let it think for a while. That didn't take long at all. 5.429 or 5.430. Okay, now region R is going to be rotated around the horizontal line y equals 4, creating a solid. Find the volume of the solid using a calculator. Okay, so I'm going to reproduce the region. Y equals 4 would be up there. This is going to require 2 radii because it's a washer scenario. It's going to have hollowness to it. Okay, my large radius is top minus bottom. 4 minus the x-axis is y equals 0. And you just thought we were done taking volumes with washers. But we're not. Okay, I can find ways to mix this stuff in anywhere. Okay. Then my small radius is top minus bottom. 4 minus bottom would be f of x. Okay. And then, so my integral volume will be pi times the integral from x equals 0 to x equals 1 of large radius squared minus the small radius squared dx. Okay, because I'm rotating around an axis that's horizontal like the x-axis. All right, now I'm going to go back in and I'm going to clear out y1 and I'm going to plug in f of x into y1 again so I don't have to type it correctly with the subtraction and the parentheses and the squaring. I don't want to take that risk. So it's going to be 12 divided by, in fact, maybe I'll even use the fraction bar, 12 over x squared plus 5x plus 6. Okay, that's in y1. And now I'm going to do pi times the integral from 0 to 1, that's 4, not 0 to 1, of 4 squared is 16, minus, and then in parentheses, 4 minus f, so that's 4 minus y1 squared dx. And I get 28.993. Okay, now we're going to compute this integral using long division. And it's like I have 1 minute till my class is starting, and, well, pardon me, everyone, I might have to... Anybody else taking the test today? Hold on. All right, so let's just do this long division. I'm just going to be brave and do it. All right, so x squared divided by x squared plus 1. Okay. Doesn't look like long division, does it? But you think, what do I multiply x squared by to get x squared? And that's 1. Okay. And then I multiply it back down, and I'll have x squared plus 1. And then I subtract all that. X squared minus x squared is 0 minus 1. So, and then that ends up being the remainder. So 1 minus 1 over x squared plus 1. Okay, you can barely even see that. Chose the wrong color. But that's the integral from 0 to 1 of 1 minus 1 over x squared plus 1. Okay, both of these are antiderivatives we need to know. We need to know the antiderivative of 1 with respect to x is x, and we need to know that the antiderivative of 1 over x squared plus 1 with respect to x is arctangent of x. And we're going to let x run from 0 to 1. That's 1 minus arctangent of 1 minus 0 minus the arctangent of 0. Okay, these, if you're not sure on why these are what they are, well, I guess you're just going to have to come talk to me about it, because I don't have time to get into that right now. And that ends, that's 1 minus pi over 4, which is a positive number. And, well, that's all I've got for you. Thanks for